Assalamualaikum. A very good morning to one and all present here. I am very much honored to thank the HR Committee of University of Technology and Applied Sciences, HCT Muscat, for providing me an opportunity to discuss about 5G wireless channel modeling as one of the emerging topic in the communication technology and networks. For the next 1 or 10 minutes approximately, we are going to discuss about the concept of wireless channel modeling. Then what are the differences between the traditional channel modeling and the 5G channel modeling, and how effectively we are going to utilize the channels for maximizing the throughput and improving the quality of service of the internet use cases with the 5G frequencies. So these are all the contents which we are going to see. Why we need 5G, in future we need this 6G. Then what are the challenges when we are realizing this millimeter wave for 5G or 6G? Why we need radio propagation channel models, and what are the different types of channel models we have, and in what way we are going to change the behavior of the channel models. Then what is MIMO channel model? Then what are the parameters associated with this stochastic based channel characteristics? And how we are going to analyze the capacity of MIMO channels based on the mathematical models what we are creating, and how we are going to test the antennas with this particular channel models. Then what are the RF design challenges suitable to this capacity of the MIMO channel? Finally, we will conclude the session. So now, what is 5G? Is it simply a 4G plus 1? Is it going to replace all the use cases, applications, network infrastructures available with this 4G? Completely no. This 5G is not simply 4G plus 1. Then what is the difference between this existing or traditional 4G network and the 5G network? So we will go back to the history. The moment first generation wireless communication systems have been developed, that is called 1G with analog models, that is used only for voice calls wirelessly. There is no value added services, even there is no SMS. Your information is transmitted in the channel, in the wireless channel, with an analog perspective. And the frequency range selected for this is based on the frequency division duplex switching, FDD switching. When we are moving towards the 2G systems, we have been incorporating slowly the data communication to the wireless networks, that is the mobile communication networks. So this 2.5G, we call it as GPRS for transmitting your or uploading, downloading your value-added services. So that is general packet radio services. So we have been adding and appending an additional data communication network with your cellular mobile communication network. When 3G emerged, we are worried about the transmission of something called the pictures, videos. But the frequency allotted for this 3G is not sufficient to carry the live video streams. So keep on, you are adding the value added services along with this mobile communication network, but the channel is not at all changed. For 1G, the same channel, wireless free space. 2G, same channel. 3G, same channel. But when 3G comes, almost 60 to 80% of the 2G towers have been replaced completely. But still even in 4G, we have emerged with 4G, we are using 4G technology, but still there are 2G towers in Oman. Not only in Oman, whole the world. Why? The service providers are not ready to deploy this 4G or 5G towers in the low density areas where the profit matters. So if they install a 5G or 4G tower in the low density area, the number of subscribers subscribing that particular network for their applications and use cases are very less, so the service provider may end to the other end, they won't get such a profit from them. So, such a low density area, still we are living with the 2G communication for voice and SMS. Unlike your 2G to 3G, when 3G to 4G technology is changing due to the technological revolution, almost 60 to 70% of the 3G towers have been completely removed. But still we have 3G towers with us. Why we need? Some of the industries, still they have their whole communication network attached with the UMTS 3G network. They don't want to replace. If you replace, you have to invest a huge money towards the 4G and 5G. That is the major bottleneck over there. Similarly, the same aspect if we think when 5G is going to deploy, even it is not going to replace 10% of the 4G towers. Why? This 5G is a new network technology. The whole infrastructure is not compatible with the 4G systems. So what is the new technological environment we have here? The 5G operates in two different frequency bands. Let us see after this slide, I will show you the frequency band and the spectrum allotted for this 5G. So it is slightly, the FR1, they call it as FR1 and FR2, 5G FR1, 5G FR2. This 5G FR1 is somewhat closer to the 4G technology. For 4G, we are having 2.4 GHz spectrum with the bandwidth of each transponder or each channel is 20 MHz only. But this 5G FR1, the minimum frequency band is 700 MHz. I hope we all remember this 2G is in the 800 MHz spectrum, 800 to 900 MHz spectrum. So the 5G FR1 is more close to the sub 1 GHz bandwidth, which is close to your 2G system. And the same 5G with FR1 frequency band B, which is nothing but 7.125 GHz, which is more close to C band, which we are using for satellite transponders, communication satellites, which is operating at the C band, 4 to 6 GHz. So these two bands are originally allotted for 5G by the 3G partnership program, 3GPP release 15. Then the researchers and the industries keep on researching or developing the devices and models for 5G, providing a higher throughput data rate in the order of 50 to 100 gigabits per second. Theoretical data rate is 50 to 100 gigabits per second. With this FR1, meeting out such a high throughput is very difficult. So what they are doing, they are simply moving the spectrum from the conventional frequency band to millimeter wave frequency spectrum, which starts from around 18 gigahertz to almost 300 gigahertz belongs to this sub-millimeter waves or millimeter wave spectrum. The problem with this millimeter wave spectrum is we have super fast data with us. Since the bandwidth is very high when you allot the spectrum in the order of 18 to 300 gigahertz. We have to put a question mark. Do we have a sufficient infrastructure to deploy that frequencies? And there is no specific channel models available to transmit frequencies in the order of 18 to 300 gigahertz in the free space. How the channel behaves when I transmit 18 gigahertz signal? How the channel behaves when I transmit 300 gigahertz signal? Therefore, the 3G partnership program release 16, they are limiting the high spectrum or high frequency spectrum of this 5G up to 80 gigahertz. But still there is a question mark. Some of the countries, they don't have equipment. So the researchers like the Ericsson, Huawei, they are still doing the research on developing such equipment which is operating on this particular frequency band. So my aim is here to give you an insight about the channel models which is used in the conventional 1G, 2G, 3G and 4G systems at a frequency ranges up to 2.4 gigahertz. And when we move to the submillimeter wave or millimeter wave spectrum, how the channel is going to modify it. And what are the new channeling methodologies or channel models you need to enhance the performance of the telecom networks. Okay. So these are all some of the advantages. As I said, it is a totally new network technology. When you go to the requirement for the 5G deployment, the first requirement is the core network. The complete core network have to be replaced with fiber optic cables. Then only at least you can able to bridge the gap between the air to the wired network. So with this consent, Oman, they are replacing with the core network. I think almost 60 to 70% of the core networks for the telecom networks by Omantel Ooredoo is replaced by the help of this Oman broadband. So even some of the cities in Oman like Sohar, Salalah, they are going to implement this project very soon to deploy this 5G use cases in those areas also. The second one, as I said, it is going to connect a numerous number of or huge number of tiny wirelessly connected devices. What is this? We are born of IoT devices. So each IoT devices are communicating each other through wirelessly, through electromagnetic waves. But each IoT device, are almost 90% of the IoT devices are operating on the same bandwidth, same frequency spectrum. So they won't interfere its operations each other. So what is the guarantee or standards given by the FCC or IEEE to maintain the correlation between the IoT devices, which we call it as EMI, electromagnetic interference and electromagnetic compatibility. So in the channel environment, if you keep on increasing the power level to communicate these devices at high frequency ranges, there is no benchmark to check the electromagnetic interference and to ensure the compatibility of the devices. And it has almost 10 to 100 times more user capacity than today due to the bandwidth. We know bandwidth is one of the parameter to enhance the capacity, not a major, but it is one of the parameter. And energy saving, it is 1/10 of energy consumption ratio than today. This is a question mark. As telecom engineers, as electronics engineers, we know that maintaining this energy consumption, you just take a simple unit from a receiver, either a receiver of your receiving your electromagnetic wave, either your mobile phone or your laptop or your tab. You can take any of the devices. The first and last stage is power amplifier. We know the power amplifiers are constructed by using non-linear devices like a BJT or MOSFET or FET. Most of the power amplifiers are nano amplifiers nowadays. Which power amplifier operates at the linear region? All the power amplifiers are operating in the non-linear region. So this non-linearity eats more of the power from the input side. So if you increase the input power, the output power has to correspondingly increase to maintain the linearity. So the regulatory limits here, this energy consumption, there is a big problem when we are moving from the linear region to non-linear region. So the benchmark is we have to operate the devices within the 1 dB compression point. What is 1 dB compression point? In the power amplifiers, we know that the relation between the linear region to non-linear region, the tolerance allowed is only 1 dB. So that is one of the limitation we have now. Then how you could able to say that we must able to save the energy in 1/10? What is the technology behind that? That we will see. Then reducing the average service creation time cycle from 90 days to 90 minutes. Even our students are doing projects using IoT. They can able to easily make such a platform to implement few use cases with the existing network along with some accessories. So like that this 5G will allow us to learn things quickly, and it will make us to adapt to the environment based on the sophistication and the user-friendly applications. And it is having 5 times reduced end-to-end latency. Here, this end-to-end latency is something different from the delay. As a definition, we know what is latency. Usually latency is nothing but the response time. In 5G, this latency is 5 times reduced than the 4G network. How they are going to provide such a response time? If you apply an input signal, the device will respond within less than 1 millisecond to produce the output. So the technology helps us to manufacture those devices. Starts from your nano chips to your VLSI ASIC chips. So that will help us to maintain this latency, so which will be enabling this 5G technology useful in the smart agriculture, smart surgery, in the real-time applications. And it will be global 5G access including low density areas. As we mentioned earlier, still we have 2G towers. Even though we are talking about 4G, 5G, 6G, 7G, still we have 2G towers in the low density areas. This 5G promises even we can able to replace this 2G towers, 3G towers in the low density areas with the affordable cost. So far, all these parameters, all these advantages, what we have seen is based on the two major resources to properly managed. One is called the telecommunication bandwidth, another one is the transmission power. So these two are the major resources for any communication system. Even this 5G is not left with these two parameters. So how effectively we are going to balance the transmission power and the bandwidth. So now let us see the frequency spectrum of this FR1 and FR2. So the 5G, as I already mentioned, is classified into two frequency bands, FR1 and FR2, according to the 3G partnership program, okay, release 15 and 16. So here you can see this FR1. This FR1 is in the low band. The frequency ranges from 700 megahertz to almost 800 megahertz, that is sub 1 gigahertz band. The advantage of these bands are long waves. The wavelengths are very long. The advantage of having long wavelengths, it can cover a large geographical area. Reason, these waves are easily penetrating through buildings so that it can cover a large geographical area. That is the main advantage. But the problem is, it is only 700 megahertz spectrum. It cannot able to bring a more data rate. So you can get a greater coverage, but the data rate, the speed or the throughput is very minimum. So coverage is maximum, but the throughput is minimum. That you can say the limitation. Advantage is it covers a large geographical area. When we move to this millimeter wave spectrum, which is FR2, which ranges from 18 gigahertz to 300 gigahertz, these waves are more prone to the obstacles. So these waves cannot penetrate through buildings. So these waves are blocked, having a large blockage, so that the coverage is very, very less. That is the major limitation of this millimeter wave spectrum. But the advantage, it is in the millimeter wave spectrum, the bandwidth is very high, so that you can get super fast data. Super fast data transmission. So throughput is maximum. In the meantime, your coverage area becomes limited. Therefore, the locally or something like an industrial environment, the agriculture field, or the smart home, smart applications, where the coverage doesn't matter, only the data rate plays vital role. So those applications, this 5G plays vital role with an application of millimeter wave. So it is not suitable for a wide coverage applications like your cellular mobile. So the comparison between this FR1 and FR2 with this 700 megahertz spectrum to millimeter spectrum, we can have a large coverage area, but the speed to be balanced, so that this FCC ITUT, International Telecommunication Union, telecommunication sector, they have been recommending a new frequency spectrum which is in the mid band, very closer to your C-band application, 4 to 6 gigahertz, which is 7.125 is the center frequency for 5G application. This will balance the speed and the coverage. So these waves may not go like FR1, but it can have at least a balanced coverage area, but it cannot get the super fast data, but speed greater than this FR1 we can get it here. So based on the applications, we have to select the frequency spectrum and the devices. Either you want data rate or coverage. If you want coverage, go with this FR1 A and B. If you want data rate, we have to go with this millimeter wave spectrum. Now the question is, whatever may be the frequency band, either it is FR1 and FR2, the channel will be same. Here you are telling it the frequency is 700 megahertz. Here the frequency is 7.125 gigahertz. Here the frequency ranges from 18 to 80 gigahertz. Are you changing the channel? Do we have any different channel modeling for this? How the channel behaves? How can we able to effectively transmit this data within this channel environment? So we have to study the channel parameters effectively to effective transmission of the data. So this is the speed, as I already told you. This 5G is promising to provide a theoretical download speed of 10 to 50 gigabits per second, which is very greater than or higher than this 4G. And the latency is 1 millisecond theoretically. 4G network, what we are getting is typically 50 millisecond latency. Now, how we are going to move from this legacy bands up to 1 gigahertz to the new band, new radio 18 to 60 gigahertz. To achieve this higher frequency rate, the peak data rate, we have to move from the traditional or conventional frequency band from 2G, 3G to the 5G, which starts with 18 gigahertz to 56 or 60 gigahertz new frequency band. What are the challenges? When we are moving from suddenly this legacy bands to the new radio, what are the challenges we are facing? The first one, as I already mentioned, there is no devices available. There is no user equipment. There is no amplifier. So we have to develop such a systems to mitigate or to realize the applications provided at this particular frequency band. These are all some of the applications of 5G, which starts with ultra reliable low latency communication use cases, then massive machine type communication like IoT use cases, then enhanced mobile broadband high speed use cases. So these three are the major use cases of this 5G system. Now let us enter into the theme of our presentation, which is realizing millimeter wave for 5G applications. As I already mentioned, there are pros and cons. We know the extremely mobile broadband opportunity, we have large bandwidth, hundreds of megahertz. This LTE has a 20 megahertz spectrum for each channel, but this 5G promises to give a bandwidth of around 200 megahertz or 100 megahertz per channel. So sometimes 5 times increase, 10 times increased in the bandwidth. So if bandwidth increases according to Channan-Hartley law, with the upper bound, with a deterministic channel, your capacity theoretically may increase or proportionately may increase, provided your channel is noise free. And you have a multi-gigabits per second data rate, flexible deployment. This is the one of the major challenge for the subscribers. What is that integrated access? So your mobile phone or your handset user equipment must capable of operating at 4G as well as at the 5G. Is it feasible to buy a mobile phone which is operating with this two flexibility with full end operation, full band operation? So for service providers that doesn't make any sense, that is not a problem to implement such a system. But for the user side, providing this dual connectivity between this 4G to 5G is a biggest challenge due to the RF interferences created by this 5G frequencies. And it has high capacity with dense spatial reuse. This is the concept. The spatial reuse concept is the It is not new technology, but still that particular technology helps us this 5G to be implemented in a better way. What are the challenges? As we already mentioned, these millimeter wave frequencies cannot travel a long distance. We know that. So that is the susceptibility to blockage will results a high blockage. Okay. The second one, as I already mentioned, the power amplifier, RF power amplifier challenges with the 1 dB compression point. I told you, linear region to non-linear region operation. So that is the second challenge. So how we are going to effectively resolve or reduce these effects to mobilize the millimeter wave spectrum? So the solutions are in threefold. The first one is intelligent directional beam forming and beam tracking through hardware or software related technology. The second one is tight interworking. That is nothing but integrated access between the millimeter wave and your FR1 B band frequency. The third one is optimizing the millimeter wave with respect to cost, power and thermal constraint. So the channel model have to be utilized in these three particular standard solutions provided by the researchers, and they are going to balance the gap between deployment and the theoretical issues. Let us see how the dual connectivity, the dual reference in the RF system will help us to enhance the communication system in a perfect way. See the first one, this LTE maximum of 20 megahertz bandwidth. So each channel is having a 20 megahertz bandwidth. How many voice calls we can able to transmit with this 20 megahertz? Assume it is a low bitrate encoder which encodes 13 kilobits per second data rate. That is the Chepstem encoder implemented in the 2G, 3G systems. So even in the 4G, still we can go with the low bitrate encoders. So with that, if you limit your voice calls with the bandwidth of with the frequency, cutoff frequency of say 3 kilohertz, we can integrate how many voice calls with this 20 megahertz channel? Will it be feasible to download a picture of say around 1 MB? So how can you relate this bandwidth with the data rate? So we have to calculate the capacity. So capacity is not only the function of the bandwidth, but the bandwidth is one of the critical parameter to affect the channel capacity. But this 5G, as giving something called a power management challenge, what is that? As electronics engineers, we all familiar when we designing an amplifier, the figure of merit is nothing but the gain bandwidth product. If you keep on increasing bandwidth, you have to keep on reducing the power. So the gain bandwidth product should be maintained as constant. Meaning that is the figure of merit. That is one of the critical parameter to be considered to design an amplifier. So here you are increasing the bandwidth from 20 megahertz to 100 megahertz. In 5G, one channel bandwidth is minimum 100 megahertz. So how your power amplifier? Nowadays we are telling that my phone have the feasibility to work with 4G as well as 5G. My phone is a 5G phone. What is the limitation they have made? How they have been bringing this bandwidth increased and your gain will be automatically decreased? Means that your service provider cannot able to provide much data rate to you at a far distance. So that is one of the critical parameter, as we mentioned here, the mobility of your millimeter wave. That's why we are telling our phone is operating with 5G, it is not at the millimeter wave spectrum. Either it may be in the 700 megahertz spectrum or it may be in the 7.125 gigahertz spectrum. So as I already mentioned, that 1 dB compression point in the power amplifier region. So we have to maintain the regulatory limits. That we have to operate our non-linear devices in the linear region. Which amplifier will provide the amplification at the non-linear or linear region? Is it feasible? We are designing a power amplifier. Are you operating in the linear region or in the non-linear region? Your active Q point will be at the center of the active region. It is non-linear. So that non-linearity provides unwanted harmonics. Those harmonics we call it as electromagnetic interference. So how do you reduce those harmonics? So that there are many solutions if you refer the research paper. One solution for this 5G, the power amplifiers, to maintain the regulatory limits, like the TRA in Oman, they have some other standards, IEEE standards, FCC standards, European standards, like to maintain the linearity limits. So these power amplifiers must be operated at a 1 dB compression point, will be the best solution to back up this particular disadvantage. Now, let us come to the real channel modeling. How you are going to model the channel based upon the based on the frequency of operation. For example, 700 megahertz spectrum is traveling on the same channel. 7.125 gigahertz is also moving on the same channel. Your submillimeter wave or millimeter wave is also moving on the same channel. So let us go back here, then I will come again. Yes, here. So this is the person from Stanford University, this Arogyaswamy Palraj. Okay, this team in the year 2004, they have developed a concept called a MIMO, multiple input, multiple output communication, and they said that it is a key to gigabit wireless. So this is the fundamental paper or fundamental work to develop this MIMO systems, and they have calculated this ergodic capacity of different MIMO antenna configuration. But the problem is, originally the theory have been modified and they have been assuming the channel is a deterministic channel. So they have applied these concepts only in the deterministic channel. What are the channels are deterministic? We can count the channel parameters. For example, one of the channel we can say it is a Gaussian white noise channel. It is a deterministic channel. Since you can able to predict the noise parameters, channel parameters easily, you are assuming that the variation of that particular noise is uniform throughout the frequency spectrum. Which noise is like that? If you take the autocorrelation function, it looks like an impulse response, a bell-shaped curve. No such frequencies or no such channel models are existing at the 700 megahertz to your 7.125 gigahertz. You can model it as a thermal noise. So if you consider your channel is a thermally affected channel, you can use this Gaussian noise or additive white Gaussian noise channel model. It is not applicable for all the spectrum. So what this particular paper has there, its own limitation. They have been calculating this gigabit wireless data rate using MIMO, but they have been assuming theoretically the channels are deterministic, then they can able to transmit maximum information based on the autocorrelation function. So they are estimating the autocorrelation function between the, yes, they are transmitting the same information from many transmitting antennas, okay, then they are receiving by many receiving antennas. What they state, keep on increasing this number of transmitting and receiving antennas. If one channel goes deeply, for example, this channel goes deep faded, the remaining channels are not get faded. This is not a new concept. We call it as rake receiver in CDMA. We know it is a fingering concept. You are transmitting channel 1, channel 2, channel 3, channel 4, channel 5. If one channel goes deep fed, the remaining or the closest channel will not get deep fed. That is the probability of error or probability of channel ergodic capacity, which has been calculated years back, 10, 15 years back or 20 years back, which call it as rake receiver. That is the concept used in CDMA phones. But here, if you assume that transmitter 1 is the active antenna, then the replication of the same information is transmitted from 2, 3, 4 transmitting antennas. So you will create multipath. Usually in communication system, we call this multipath as a challenge. We have to reduce the multipath. But in 5G, we call this multipath as advantageous. This multipath will create a multiple channel environment, will increase the capacity. So the challenge is converted into advantage here, but the problem is how effectively you are going to create uncorrelated multipath channels. So usually multipath is a disadvantage in communication system, but in 5G this MIMO, we are taking this multipath as the advantageous one, but only problem is, or only challenge is, how far these multipath channels are spaced. That we call it as spatial reuse. So the analysis of this particular channel modeling is based on the space-time coding. So space plays vital role, how effectively you are putting the transmitting antennas with reference to 1, with reference to 2, with reference to 3 to create multipath or uncorrelated multipath. So there are different channel models we have been come across during the implementation of this wireless cellular network from 2G to 3G, 3G to 4G, 4G to 5G. We can see here, this is a fixed wireless, your normal wired telephonic network. We consider it as a fixed link. The parameters considered is only power or the path loss. When it is coming to 2G, we are giving the parameter which is called Doppler shift. When you are allowing the mobile user to move, so the convolution of multiple emitted signals will create a large multipath, will reduce the received power at the receiver. We know that matched filter concept is the suitable concept to determine the or to estimate the received power. So that mathematical modeling we might be studied in matched filter concept in DSP or digital communication. Then slowly, when this 3G comes with a wide bandwidth, here instead of time division duplexing, we have to talk about frequency division duplexing, and delay becomes the large parameter to analyze the channel. Then when it is coming to 4G, MIMO have been introduced, but it is not a multi-user MIMO, it is a single user MIMO. So for a single user MIMO, we have a lot of parameters, characteristic parameter to analyze this channel. One is a spatial correlation, angular spread, and polarimetric models. So these three are the major constraint when we are implementing single user MIMO. When it is 5G, it will become a lot of input parameters, or you can have a more number of degrees of freedom to design your system in an effective manner. What are the freedom you have? One is millimeter wave, another one is dual mobility. What is dual mobility? In mobile communications, only the receiver, the user is allowed to move, your base stations are fixed. But in 5G use cases, you are allowing both transmitter and receiver to move. So the channel model is updated at the transmitter end as well as at the receiving end. So we have to incorporate the correlation parameters with the transmitter as well as the receiver. It is not a simple task to allow the transmitter to move with respect to multiple scatterers surrounded by the receiver. So we have to calculate the stationary and non-stationary parameters and spatial consistency. What is the spatial consistency? For example, I am going to implement 4x4 MIMO in the base station. Base station has a huge number of, our space is not a problem. You can able to implement around 32x32 antenna, 64x64 antenna. But take your user equipment. Where is the space to provide uncorrelated path within the small mobile equipment? Or your tab or laptop, is it possible to provide certain limitations with respect to the spatial correlation? Then how do you maintain the correlation parameters to obtain the bandwidth? So these are all some of the limitations when we are modeling the channels, and what are the features we are going to incorporate. So these are all the requirements, new requirements when we are going for the 5G channel model. One is the wide frequency range, the broad bandwidths, wide range of scenarios, then double directional 3-dimensional modeling. The double directional, as we said, both are moving, both transmitter and receiver are moving with respect to the scattering parameters. Then a smooth time evolution, a spatial consistency. This is the one we are going to concentrate today. How we are going to maintain the spatial consistency between the transmitting antenna and the receiving antenna when we are implementing this MIMO receivers at the different use cases. The next one is frequency dependency and frequency consistency. Here I want to stress one point. We know that there are two different types of channels. One is frequency flat channel, another one is frequency selective channel. Hopefully, if you refer the mathematical model for the frequency selective channel and frequency flat channel, you could able to identify the two major parameters between the frequency selective and frequency flat. Flat frequency channels is assuming that the scatterers are at the fixed locations, and it starts to calculate the convolution between the transmitted signal and the received signal. But in the frequency selective channel, you are going to apply the concept of resonance. At least one particular frequency becomes maximum, assuming the all other scatterers are out of band. This is the theory. How you are going to bringing back the theory to the practical illustration. So what are the statistical parameters, channel parameters are adopted to calculate those particular parameters. So the next one is the massive MIMO. As we said, MIMO is something like a limited number of antennas. Massive means it is a huge number of transmitter and receiver. 32 cross 32, 64 cross 64. So in the transmitter side 64 antenna, in the receiver side 64 antenna. So how many multipass we can encounter? 64 NC, 64 combination like NCR. So then we have to allow the two parameters, which is called as stationary and non-stationary parameters. And this array optimization, we are not considering the antennas as array. We are considering the antennas as MIMO. So array concepts are slightly modified to reconfigure your antennas from array to MIMO. So these are all some of the requirements for the 5G channel models. The next one is the high mobility. For example, this electronic warfares, where your commander chips are moving or your commander vehicles in the electronic warfares are allowed to move with a high speed. You know, in some of the cities like China, South Korea, they are providing internet in the metro trains. We know the speed of the metro train. It is moving with very high speed. How they are providing, how many base stations are there inside your metro train to provide high speed internet access? High speed in the sense of data. I'm not telling about data. Your vehicle is moving with such a high speed, but they are providing your internet access within the metro. How is it possible? So how we are going to use this high mobility as one of the parameter? This 5G channel model should support high mobility scenarios. So that is HST, high speed trains. So which is moving with a speed of 500 km per hour. So can you able to calculate the sensor models or antenna models which is transmitting only two parallel path with a speed of around 500 km per hour. So your T will be 500 km per hour, okay, distance traveled, and time is within fraction of second. We know the speed of electromagnetic wave. It is equivalent to light speed, 3 into 10 power 8 meters per second. Will you calculate the delay encountered by this particular system? What is the maximum delay we can encounter when the train is moving with the fixed mobile station? It emits an electromagnetic wave, and once it emits, the train will move almost 3-4 kilometers away from that. Will the user get the information? So how we are going to bridge this particular or remove this particular challenge or resolve this challenge? So we need to consider all these parameters as the realistic models, and you have to come with a new channel model to incorporate these particular parameters along with the conventional radio channel models. That's why the Rayleigh, Raytheon, Okumura, free space path loss models are reference models. We have to take each model based on the requirement, and you have to modify the channel characteristics based on the frequency, speed, and the new requirements adopted for this 5G channel models. That's why in the deployment of 5G, still there are more number of bottlenecks, those bottlenecks to be removed by means of suitable research. So these are all the latest literature. This has been published in the year 2016, February 2016. After that, there is no proven result for certain movement of this recent advances in the MIMO channel measurements. So these are all some of the antenna models. These are all some of the channel characteristics. They have been proved, and all this paper I have given as the reference at the end, or you can open this link and you can see these are all the MIMO channel measurement and models. So these models are already proven with respect to a speed of around 80 to 120 km or 140 km per hour only. but we need a new models which is supporting with a speed of 500 km per hour. Okay, so how this characteristics of this particular high mobility channels with large Doppler frequency and non-stationarity is included. So what are the effects we are going to consider when we model these channels? So let us go to the three-dimensional space-time frequency models for wide sense stationary uncorrelated scattering. What is this uncorrelated scattering? As we said, this MIMO will create uncorrelated path to enhance the capacity. So we have to adopt this wide sense stationary uncorrelated scattering condition. So we have to take the existing 2D models and you convert that existing 2D models into 3D models by using suitable mathematical converters, transforms. Earlier, for image transformations, we are using simply discrete cosine transform or discrete Fourier transform. But those basic transforms will not help us. So we have to go with the Hilbert transforms or advanced Hilbert transforms to mitigate the effects of this 3D space-time frequency channel models. So some of the channel models are in time domain, some of the channel models are in frequency domain. So whenever we are considering the Doppler frequencies and delays, better to go with the frequency based models. Remaining, you can go with the time domain models. Even you can able to convert this formulated frequency domain models into time domain model by adopting suitable Fourier transformations. Either you go with the fast Fourier transform or you go with the conventional discrete Fourier transform based on the application. So we used MATLAB to simulate these models. All these 8 models we have simulated, okay, and the reference is in the year 2018. After that, after this paper, we have been simulated all the existing 2D models and we have converted into 3D space-time frequency models. I will share my results which has been published already. Before sharing, usually in any of my talk I include this particular parameter, particular Shannon information capacity theory. So we are telling that this particular equation is suitable up to a channel having capability of one path. If we have multi-path, this particular parameter, this logarithmic scale, your capacity increases or grows with respect to logarithmically. But this with this MIMO, these people, this Arogyaraj and Arogyasamy, Palraj and team, they proved that this capacity of channel capacity grows linearly, increases linearly. Instead of logarithmic, it grows linearly by simply increasing m and n. So they are not telling that this equation is wrong. They are telling that logarithmic scales are always compression scales. Logarithmic scales are always compression scales, so that based on this SNR, the signal power is always compressed. You cannot go beyond a certain limitation of this capacity even though your bandwidth is increased. So in 4G, this particular bandwidth is increased for the given SNR by means of carrier aggregation concept. It is nothing but increasing the number of frequency blocks for the required user. For example, I am a user. Initially, I got a bandwidth of say 20 megahertz. Now, I feel that the bandwidth which I bought from the particular service provider is not sufficient. I am going for enhancing my data rate without paying much money. So, they are allotting a frequency blocks to increase the bandwidth, which we call it as femtocell concept. This is true only for fixed wireless access. If the user is moving, this particular femtocell concept may not help us. So this is used only in the fixed access points like your ADSL modem. If you want, they are telling 26 OMR plan, 35 OMR plan. What is that? They are simply appending the frequency blocks with your fixed wireless access network and they are charging accordingly. So that concept is called carrier aggregation in 4G. That is with a single user MIMO. But in 5G, they are using something called massive MIMO, which is multi-user MIMO. So where this femtocell concept is not utilized, they are simply increasing the number of transmit and receive antennas. You can check, there are many use cases they kept in Huawei, Omantel, and one more place in Oman. They have been implemented this particular 5G with 7.125 gigahertz band and 18 gigahertz bandwidth, okay, 18 gigahertz spectrum, and they proved that the capacity is also somewhat greater than this linear increase instead of logarithmic. So we have modified this equation. We took this as the base paper. In the paper, they have assuming the channel is a deterministic channel, and they are calculating the capacity, and they proved that the capacity is increasing linearly with respect to the given SNR. But what we did, we changed this deterministic channel nature into, so what we have done, we have changed the deterministic channel into a random channel. So first we assumed the channel is a frequency flat channel. We changed this equation to frequency flat to frequency deterministic to frequency flat. Then how we are going to modify this? So the modification is done in terms of a correlated channel environment. Yes. Here we have been incorporating the impulse response of the channel, and we are calculating the autocorrelation function at the receiver side, and we are calculating the autocorrelation function at the transmitter side, and we have been replacing this HSS equation with respect to the autocorrelation matrix given by this Arogyasamy Paul-Raj paper. So what we have done, we have been changing this Hermitian matrices from their equation, and we have been incorporating our conditions based on the channel models what we are assuming. Then we have started our simulation. So we have been using this MATLAB to calculate the effective cross correlation. As per the theory by Bowser, and before Bowser there are Okumura, Nagakami, there are a lot of channel model parameters. What they have been using, they are using S parameter approximation for analyzing the channel. The disadvantage of this S parameter approximation, during those days it is advantageous, since it is isotropically radiating its electromagnetic power, meaning it radiates uniformly in all directions. That is their assumption. But in 5G or in mobile communication, you have to create the beam. The desired power is directed towards the intended user, not to all the user. So you have to go with the directional beam forming. So this S parameter approach is not a suitable approach to model your 5G channels. So that we have been moving towards the separate channel model to analyze the effective cross correlation. One of the channel model given in the literature is employing diversity technique, or you can simply change the antenna configuration. So in the year 2007, we took up some small research by changing the diversity technique. Instead of employing a Rayleigh channel, we have been modeling a Rizian and Nagakami channel with respect to the Hermitian matrices. We proved that changing the antenna configuration is one of the solutions to provide or to measure the effective correlation to enhance the capacity. So we can see how many correlated environments we can generate, and we could able to calculate the spatial correlation by evaluating the output performance with the smaller spatial correlation. So here the spatial correlation is one of the parameter we took up which affects the capacity of MIMO system. For example, a 4x4 MIMO, we'll come back again those equations. For a 4x4 MIMO, we have 1, 2, 3, 4 ergodic paths to carry the information. Irrespective of the eigenvalues, it is nothing but simply we are not calculating the magnitude, you just see the path. Here we are assuming this is without correlation. So the eigenvalue distribution of 4x4 MIMO, and we have modeling transmitter 1, the first antenna is the active antenna, remaining antennas are passive, no information is transmitted. So using this approach, we have been evaluating the spatial correlation with respect to the electric and magnetic fields radiated by the antenna. We assume that there are 20 scatterers, meaning 20 other mobile users along with the intended user. Then we check the power received by each mobile user by simulating this particular environment, and we took up the theoretical concept which is given by the Balanis. Okay, so this particular equation we modified only the delay performance here. with respect to the electric and magnetic field, and we calculated the two parameters. One is with respect to cosine angle, another one is with respect to sine angle. The cosine angle, we know that it is a even information. Sine angle, it is nothing but an imaginary information. So we divided the power into real power and reactive power. Reactive powers we don't calculate for antennas. Reason, it is capacitive or inductive power. Energy will be stored over there, but my antenna has to release the energy, so that we are not incorporating those parameters like a inductive or capacitive resonance. We are taking only the resistive parameter. So we model antenna as a resistive model. So that's why we used to calculate the radiation resistance of the antennas. So using that, we are dividing the spatial correlator into two parameters. One is with respect to real, another one is with respect to imaginary. Then using that, we are calculating the simulation setup by calculating joint spatial power spectrum. One is with respect to zenith angle, another one is with respect to the azimuth angle. One is for electric field, another one is for the magnetic field. So this is the model what we have been done with respect to the spatial correlation by increasing the spatial correlation from 0.5 to 1 lambda, 1 to 1.5, 1.5 to 2, up to 3 lambda distance with different azimuth and elevation spectrum. We found that this azimuth angle of 45 degree and elevation of 10 degree with an antenna correlation parameters at 1 lambda and 1.5 lambda outperforms than the other scattering parameters. So this is the condition till now we are using to create antennas. Even HCT, there are two batches of my project students, they developed around 45 simulations based on this particular 1 lambda and 1.5 lambda distance. Still we are not getting a fruitful results to implement those antennas in the real time. Reason, this is the reason when we are selecting the microstrip as one of the tool to implement the antenna with respect to 0.75 lambda distance or 1 lambda distance, we need at least 12 ml thickness of the substrate material. So there is a lagging of substrate material, so that still this particular research is under paper. It is not implemented as a prototype. So this is the mean capacity as a function of SNR. Here we have been proving this particular result of the fundamental paper. Yes, we are proving this fundamental paper. They are telling in the year 2004, these parameters are increasing with respect to capacity for deterministic channel. So we developed our own antennas. We proved that for random nature, when you select a suitable microstrip antennas, you can able to provide the same performance with respect to your microstrip or dipole, so which will be giving almost same characteristics, same antenna characteristics with respect to the SNR. The capacity is also same. So we have to be select the channels in a proper way that could mitigate the theoretical approach to practical approach, and we can balance both the things. Then we have developed a few models. Instead of using a rectangular microstrip, we have been selecting a circular patch, and we are not using array, we are not using MIMO, single antenna with different switching characteristics. So we are going to change the switching pin. See, the same antenna, circular microstrip antenna, we have two feed, coaxial feed. If you feed simultaneously these two antennas, this behaves like a MIMO antenna, meaning that you can able to transmit two different paths. Instead of having a two different antenna, a single antenna will produce a multi-mode application. So this is one of the suitable solution to provide, to provide a sufficient channel characteristics, and we have been using this particular array, four element array and a multi-mode antenna with the same channel parameter. We estimated the channel model using Kronecker, same approach. We proved that the multi-mode antennas provides the modes at the transmitter and the modes at the receiver. I think the third one from right, this one will provide, this is the modes at transmitter and modes at receiver, provide optimum capacity, and the capacity reduction is only here 13 to 11. So only 2-bit reduction in the capacity, so multimode antennas also suitable solution for the user equipment. But the problem with this multimode antenna, maintaining the R by D ratio for the EMI EMC concept, it should be at least 0.7. If we maintain this R by D ratio 0.7, you have to provide the receiver location at 2 lambda, transmitter location at 0.5 lambda. This is practically not possible. So we have to go back this transmitter correlation effect. No, it is not sleeping. I'm using this now. Yes, sir. I'm sorry. So now you could able to see that the capacity is almost the same for the given probability of error. So when we compared with this array antennas, this multimode antennas behaves in a different manner. So let us come to the conclusion. So far I have given overall insight about the 5G techniques and its 5G technology and the corresponding channel models. So still it needs to be analyzed in terms of various frame structures, multiple access techniques, channel coding and spectrum. So here we are assuming the transmitter, the baseband communication systems are already developed. Then we are checking only the electromagnetic characteristics of the channel behavior with respect to millimeter wave frequency and the midband frequency. But still we need to analyze the baseband analysis in terms of frame structures, multiple access. Either you are using your frame like your normal DLC layer or normal LLC layer based on the physical layer performances. We have to modify the entire coding analysis to get the optimal optimal performance of this 5G network without sacrificing the quality of service. Okay, so these are all my references. These two are our research paper, this 4th one and the 5th one are our research papers where we have been incorporated this multiple input, multiple output for 5G in the year 2011. So during that time we took up the frequency ranges in the order of 6 gigahertz. But later on in the year 2016, 17 and 18, this 3G PP group released 17, they have been increased the frequency range. So what we are doing now, we are evaluating the same multiple input, multiple output system with that particular frequencies. Our paper will not work for that particular frequencies. Reason, there is a large gap in the assumptions. So we have to go back and redesign the system to achieve optimal performance. Thank you so much for your patient listening. If you have any queries, you can ask. Sir.
Thank you for your wonderful presentation. I would like to know about the things or design that 5G or 6G has tried to implement so that the rain effect will be minimized. Because as you know, as rain is coming in and the signal is going to be in gigahertz, like more than 10 gigahertz, the problem is the signal is going to be very, very small as it travels from one place to the other.
Yes.
And if that rain is going to be as much as, or as big, or closer to as big as that signal, then the signal will be cancelled out.
Yes.
So what does 5G do? It will eliminate or minimize the effect?
It will minimize, sir. Based on the literature review, you can see this 4G is operating at 2.4 gigahertz with the devices which they are manufacturing now, with the Doppler shift up around 0.1 millisecond to almost 30 milliseconds. They are incorporating the latencies with the end user devices. That's why when rain comes, if a signal is disturbed or distorted at that particular timing intervals, is also preparing or incorporating its coherence bandwidth, so that the coherence bandwidth automatically will be getting increased based on the delay. Okay. But this 5G is far away from that particular frequencies. For example, if you take millimeter wave frequencies in the order of 18 gigahertz, you can calculate the time which will be retarding with respect to one unit element to another unit element, which is somewhat 10 to 15 times greater than the 4G networks. So that if you have a suitable, yes,
Signal is going to be very, very small.
that's why. The thickness of the boards which we are fabricating now for the substrate materials, which will be radiating its electromagnetic energies in such a way it will be transmitting with low latency. So the rainy signals which are all dropping, so when it touches at this particular point, okay, so it will be diversified or it will be scattered with the many waves. But the frequencies in the millimeter waves, it won't allow those signals to scatter much more based on the wavelengths of the water content. It will be moving with respect to complete attenuation or 30% attenuation or 20% attenuation. So that effect will be minimized. Instead of more than 50%, it will be less than 40, 20, 30% eliminations or limitations in the attenuation level with the water content.
So what will happen to the scattering in the signal is cancelled out?
So still you will create a multipath.
No, because signal is cancelled out because of...
It is not cancelling, it is scattering.
Yeah, I know. So when the signal enters, yeah, and there's a huge rain there,
Yes, sir.
so there's a possibility that the signal will be cancelled out.
That's why it is not cancelling. It is going, if it is cancelling, when it is going more than 50% attenuation. When it is going more than 50% attenuation, the signal will not reach. Like what this 2G, 3G is doing. You won't get the signal. Sometimes you will get a distorted signal, sometimes you won't get the signal, your call will be cut. But it is not like that. You are creating multipath. The scattering also multipath scattering. This is a MIMO channel, sir. Same information is transmitted, is like that. So same information is transmitted in 4 pathways. So if one goes deep fed, the other will not fed. That is the concept of diversity. That is the advantage of 5G. So one channel goes deep fed, at least the strongest signal will reach or will go with any of these 3. If all 4 channels are distorted, you won't get information. Even there is no guarantee for that. That is the concept. Yes, sir.
Thank you, Doctor. Thanks everyone for coming. Actually, check please your email. It is correct or not, because we're going to send the feedback of that email, and after you fill the feedback, you will get the certificate. Okay? Thanks for all of you, and thank you, Doctor. Interesting topic actually. Yesterday I was in Orido in a hall, and one customer, they asked why I apply 5G and it's not working in my home, and I need 4G again to be. So that's time I thinking why 5G sometimes is not working in some place and 4G is more better than 5G. And today, mashallah, you give me a lot of information about
Yes, ma'am.
this.
Thank you.
Thanks, everyone.
Thank you so much.